name is Michael Hepner from Old Dominion University, and as part of my senior project I decided to build a coil cannon. A coil cannon is like a rail gun, except that it uses an inductive coil to shoot a projectile. Going to buy the parts for this, I couldn't find it all at just one site, so it took actually a couple days in order for me to get everything that I needed, especially to the specifications that would work for my particular design. And so that was the first difficulty, trying to find all the parts. And even then, it was a while till I actually got the big bank capacitors, which you will see later, which are the big blue ones in the middle of the board. After getting the parts, the next major difficulty was trying to fit the littler capacitors on the circuit board. That was a very tight fit, and I am thankful that it was actually able to fit, but it was basically snap-ins, and they don't get going very deep, so what I had to do was to solder extra wire to it to make sure that there was good connection to the breadboard, and so that I could make sure that the circuit would work correctly. The little capacitors, as you will see right here, is part of the pentuplar voltage multiplier, which creates, or from the 120 volt source AC line, it converts that to, or from basically goes into DC mode, and it will multiply that voltage up to my specifications, which is 800 volts. Why 800 volts? That's because if it goes any higher than that, then my capacitors might explode, and I don't want that to happen. Although it would be a nice firework effect, so I'm sure, but I don't want to test that right now. All in all, I would say that this took about $500 out of pocket in order to build and order all the parts, and it's worth it. Just have to make sure to keep on maintaining afterwards. The next major difficulty would be the wiring the capacitor bank, because it needed extra thick wire, 12 AWG, in order to handle the massive current spike in the triggering process. And so from the capacitor bank to the actual inductive coil, it had to be 12 gauge wire, and then from the capacitor bank to the pentuplar voltage multiplier on the breadboard behind it could take a smaller wire, like 22 gauge. The next major problem was the SCR, the silicon controlled rectifier. At first I had a problem with trying to wire it correctly, because I got the cathode and anode mixed up, the positive and negative leads, and also the lead that would go to the trigger that would actually fire the coil cannon. But so after that was figured out through some trial and error, that was no longer a problem. And thankfully, I originally thought that I had bad SCRs, but it just turned out that I just had it connected improperly. Right. And then in the actual testing stage, at first we were able to get it to work, but then I don't know what happened, but it decided to go towards Murphy's Law and then not work anymore the next day. I didn't change any of the wires in. I'm still not sure exactly what it was, but it wasn't working, so I had to troubleshoot. And again, one of the other problems I found out was the SCR was wired incorrectly, and also I was grounding it when I should not, which it was, the design is basically a floating ground circuit, so it didn't actually have to go back to actual ground by the way it was wired. And so after that, and making sure there was the right resistor next to the trigger, because if it was too high of a resistance on the trigger, then it would not release the current correctly. It would not fire correctly. So I had to make sure to bring it down to a little bit lower resistance next to the trigger. So after that, everything was working good, and that's pretty much does it for the actual problems. Alright, I'll talk about the individual parts now, starting from the inductive voltage multiplier, going on through the capacitor bank and then the inductive coil. And actually before all that, I think I should also talk about the actual power supply. My power supply is a 120 volt AC variac, which converts the AC line to DC, and it's a step up power supply, so it goes up to 140 volts DC. And this allows me to increment up slowly the voltage, and also allows me to control the current so as not to burn out my circuit. The trigger mechanism cannot handle any more than 3 amps, and so as long as I turn up slowly, then it won't be a problem, and it will not open my circuit, which of course would be a bad thing. And so the actual triggering device is normally open, and so when I close it, it just completes the circuit and allows the current actually to spike and go through the coil, firing the projectile. And so once the voltage, at first the voltage goes through the inductive voltage multiplier, which is a combination of diodes and capacitors that takes that power source and multiplies it up to my specifications is 800 volts. Any more than that, then the capacitors, bank capacitors might catch on fire. And so once it goes through that, then it goes, like I said, to the bank capacitors, and the capacitance rating on that is 1,900 microfarads. And with the series and parallel combination, it allows me to go up to 800 volts as well, even though a single capacitor is only 400 volts. And once the capacitors are fully charged, and I release the trigger, it doesn't go all the way down to 0 volts. There's still some residual charge left on the capacitors. It's just a natural property of the capacitors itself that it kind of warps the charge it has. It's not a physical warpage, but it's just a charge. And so afterwards, just make sure not to touch the pins or whatnot, because you might get shocked. But it'll be much smaller, maybe 20 volts or so. And so coming from the capacitor banks, again from here we'll have the heavier gauged wire, and there's a 12 gauge wire going down to the inductive coil, which is about 5 inches in length, and the projectile has to be sticking out a little bit on the capacitor side. Otherwise, if you don't do that, then it would just run into the capacitors, because when the electromagnetic field is created around the coil, it will draw everything towards the center of it. And so actually, the projectile is being pushed about halfway into the center of it, and it just keeps on going through the momentum. And so just as a safety precaution, just make sure there's about a little bit left sticking out towards the capacitor side, so it'll go in the way that you want it to. And that pretty much does it for the parts, besides the actual projectile. The projectile is 5 inches in length and 8 millimeters in diameter. And I chose that particular length so that it would have more time and actual substance for the magnetic field to push through the coil, and which should give me a higher velocity. And the velocity should be around 80 miles per hour, once it is fully charged.
Okay.
Loading it in. I'm going to crank this up until it hits about 200 volts. Once I do that, I have to turn this to 0 and then press the trigger so that it doesn't keep on charging. But the capacitors have some drain to it, so I have to do it pretty fast, otherwise I'll lose the voltage. Here goes the first trial run of real projectile. Again, I'm going to 200 volts. Alright, fire.
Nice!
Yep. Going up to 300 volts. All clear? All clear. Nice. Let's go to 400 now. Clear. Oh, clear. Clear. 600 volts. Clear.
Holy cow. That nailed the trick.
Oh, clear. Nice. Alright. Oh, clear. Oh, clear.
781, 787.
Alright.
Nice. 770.
Go.
Holy cow. Look at that.
Alright, success.
That's in there really good.
Yes, okay.
That was really solid into that tree. Look at this divot it made. Right there.
Holy cow.